Hi class, my name is Justin, and today we'll be covering section 7.4 trigonometric substitutions. So the basic premise is this. So far, whenever we had integrals in which we had in the parentheses like x squared minus 2, this was raised to the third power, we would normally have to FOIL this out in order to distribute that cube into this entire term in order to get a really complex polynomial. However, we then learned u substitution, in which we had a particular case in which if we could set u equal to whatever was inside the parentheses or whatever inside the radical, and the derivative of that term, the du, happened to be something that existed in the outside of that term, which was also located in the numerator, then we were able to have this shortcut such that we set u equal to x squared minus 2, du is equal to 2x dx, and as a result we were able to simplify this composite function as the integral of u to the third power du, which we can then solve as 1/4 u to the fourth power plus c. In another example, we have the integral of 2x over the square root of x squared plus 4 dx, and we see here that the same situation applies here. We have to do a very intelligent u substitution such that when we set u equal to the radicand, the x squared plus 4, du happens to be equal to 2x, which allows us to then replace this as the integral of 1 over square root of u du, which we can solve as the square root of u with a 2 in front, with, of course, a plus c. So now we will get into situations of trigonometric substitutions in which that we'll look at one of the three main categories, the integral of 1 minus x squared dx. Not surprisingly, this integral is not going to be able to be solved using a previous method that we had. We can't use integration by parts. We can't use anything that we know at this point. But what we want to do is we want to do some sort of u substitution, which is not necessarily u. In fact, what we're going to do is we're going to look at this radicand, 1 minus x squared, and recall back to the idea of the trig identity such that sine squared theta plus cosine squared theta is going to be equal to 1. In the previous section, we learned that the derivative of sine is going to be equal to cosine. Likewise, the derivative of cosine is going to be negative sine. And that allowed us to do these really funky integrals. Now, what I want to draw your attention to here is, let's suppose that we rewrote this so that sine squared theta is equal to 1 minus cosine squared theta. Notice how this 1 minus x squared, if only x were equal to the cosine of theta, what that'll allow us to do is to then rewrite this entire radicand as 1 minus cosine squared, which was going to be equal to sine squared theta, and that'll fit the radical, because then the radical of sine squared is going to be just equal to the sine. And that's in fact what we're going to do. And this is going to be x substitution, not u substitution. And the difference is that when we do x substitution, we can directly solve for dx, which is going to be negative sine theta d theta. Now check that out. Typically for a u substitution, you have du related to some function of x dx, in which we then had to divide so that we only included a particular term on the right hand side. For example, in these previous problems, we had u is equal to x squared minus 2, and by taking the derivative we had du is equal to 2x. Had this term been something different than 2x, we would have to divide both sides to make it fit, and we might have replaced that entire numerator and the dx into probably negative du, 3du. But in fact here all we're going to do is replace this entire dx with negative sine theta d theta. Now the 1 minus x squared, because x is equal to cosine theta, this becomes radical 1 minus cosine squared theta times, now dx is going to be replaced with negative sine theta d theta. As a result, the 1 minus cosine squared theta becomes sine squared theta under the radical with a negative sine theta d theta on the outside. And what we see is that we take that radical of the sine squared theta to become sine theta times negative sine theta d theta, which we have to take the radical with. Which we have to take the integral with, and we get sine squared theta with a negative outside d theta. That is what we need to solve. We just learned the reduction of power rule from the previous lesson, in which case this is now negative the integral of 1 plus cosine of 2 theta all over 2 d theta, and this is definitely an integral we could solve. We get negative 1/2 integral of d theta, just for that first term, minus 1/2 integral of cosine of 2 theta d theta. And the first term is just going to be negative half theta, because now our variable of integration is going to be theta, minus, and here we're going to get 1/4 sine of 2 theta plus c. So the question is, what is theta? Well, remember back from our substitution, we had x is equal to cosine of theta. If we wish to identify what is theta itself, that'll just be the inverse cosine of x is going to be equal to theta, and that's going to be what we substitute into both of these. So therefore we have negative half arc cosine, or inverse cosine of x, minus 1/2 sine of 2 times the inverse cosine of x, plus c as your answer. So let's come up with a general rule on how to solve these sort of integrals. So if you were to have the square root of a squared minus x squared, the idea is you set x equal to a times sine of theta. So for example, if I had the square root of 5 minus x squared, the idea is that the a squared is going to be equal to this 5, so that if x is equal to square root of 5 sine of theta, then what that allows us to do is x squared is going to be 5 sine squared theta, and when we replace this x squared with this term, we get 5 minus 5 sine squared theta, all under the radical. And in fact, we can momentarily factor out the 5 under the radical to get 1 minus sine squared theta, which then will become radical 5 times cosine squared theta, which then only the cosine squared will be simplified as rad 5 times cosine of theta to the first power. So it doesn't really matter what the term is that you're subtracting from the x squared. Whatever that number is, that's going to be the a value square rooted, of course. So let's look at the example that we have in the book. The book provides with us an integral such that the integral of a dx in the numerator and the denominator, we have x squared square root of 4 minus x squared. And we see that the a squared term in this case is going to be 4, so a is going to be equal to 2. And what we'll do is we'll set x equal to 2 sine of theta. Therefore, x squared is going to be equal to 4 sine squared theta. And when we do our substitutions, well, going back to this, dx is just going to be equal to 2 cosine theta d theta. Now, this 2 cosine theta d theta will replace that x in the numerator, and so we get 2 cosine theta d theta. What's really important is that we get rid of that radical term, and when we replace the x squared with the 4 sine squared theta, we're going to get 4 minus 4 sine squared theta. But this additional x squared term that we have in the denominator, that's just going to be 2 sine theta squared. So I'll put in parentheses 2 sine theta squared. Now, this entire radical, if we follow this same notion, what we expect to have is radical 4 times cosine of theta. And so we have the integral of 2 cosine of theta d theta times 4 sine squared theta, and this is going to be radical 4 cosine squared theta d theta. This is going to simplify to 2 cosine theta d theta all over 4 sine squared theta times 2 cosine theta. And in fact, the 2 cosine theta in the numerator and that of the denominator disappears. So really all we have is 1/4 the integral of cosecant squared theta d theta. And we do know what this integral is going to be. In fact, it's just going to be negative 1/4 cotangent of theta plus c. But what is this theta? Well, earlier we said that x is equal to 2 sine of theta, and when we solve for this, we get x over 2 is going to be equal to sine theta. Now, in geometry, we learned that sine theta is just going to be opposite over the hypotenuse. So if we were to imagine a triangle with an angle of elevation as theta, then the opposite side over here would be the x, and the hypotenuse would be 2 respectively. That tells us through the Pythagorean theorem that the missing side can be solved. If we do 2 squared minus x squared square rooted, then we get the square root of 4 minus x squared. And so the cotangent of this particular triangle would be the adjacent over the opposite side, so that our answer is going to be negative 1/4 square root of 4 minus x squared all over x plus c, as we see from the answer here. Let's do an example, particularly number 10. This looks like a very challenging one. So we have the following. We have the integral of x cubed square root of 5 minus x squared dx. The idea here, we will set x equal to whatever the square root of this number, square root of 5 sine of theta. And as a result, we know that dx is going to be radical 5 times cosine of theta d theta. That will replace this term. X squared will be the 5 sine squared theta. And we can also figure out what is x cubed. X cubed, I think, will be 5 to the 3 over 2 power, because this radical 5 is going to be 5 to the 1/2, and we have sine to the 3rd power. So let's see what we get. So first we get the integral of 5 to the 3/2 power sine cubed theta. Then under the radical we have essentially 5 minus 5 sine squared theta. That's going to give you 5 cosine squared theta. And the dx is now replaced with another radical 5 cosine theta d theta. And when we simplify that, we will essentially get 5 to the 3/2 power sine cube theta. This will be radical 5 times cosine of theta, which then multiplies to another radical 5 cosine of theta d theta. And so what we have here is we have 5 to the 3/2, 5 to the 1/2, 5 to the 1/2. That looks like 5 to the 5/2 power. And notice this is just a constant. We could have even taken this out of the radical or the integral. And we have sine cube theta times cosine squared theta d theta. So we have a situation here in which the odd term in this case is going to be the sine. So therefore, we're going to essentially do a secondary set of substitution, because we know that sine squared theta plus cosine squared theta is equal to 1. We're going to take one of the sine squared thetas and turn it into 1 minus cosine squared theta. So as a result, we get integral of 5 to the 5/2 power. Now we're going to write this as sine of theta times sine squared theta, because that is going to be equivalent to sine cubed, times cosine squared theta d theta. And so here, let me just take the 5 to the 5/2 power outside. Integral sine of theta, we have 1 minus cosine squared theta times cosine squared theta d theta. And since we first did an x substitution, now we're going to do a trigonometric substitution that we learned from the previous section, in which I will now indicate in red, or I guess pink, is that u will be equal to cosine theta. Du is going to be equal to negative sine theta d theta. So therefore, we have sine theta d theta is going to be equal to negative du. That'll take care of this, that'll take care of this. So we have negative 5 to the 5/2 power integral of 1 minus u squared times u squared du. We could distribute this u squared, so we get negative 5 to the 5/2 power integral of u squared minus u to the 4th du. And so that gives me the following. So we have negative 5 over 2. Inside the brackets, I'll have 1/3 u cubed minus 1/5 u to the 5th power plus c. The u was equal to cosine, so when I first put those in, I get negative 5 to the 5/2 power, 1/3 cosine cube theta minus 1/5 cosine to the 5th power plus c. And let's go back and see what this theta is related to. And I'll use that as a different color, like purple. So here what we see is that the original function was that x is equal to radical 5 times sine theta, or in this case sine of theta is going to be equal to x over radical 5. And if we draw that triangle, we have the angle here, the angle of elevation. The opposite side is going to be x, and we have the hypotenuse is going to be radical 5. So when we then use the Pythagorean theorem, we will get the missing side will be equal to 5 minus x squared, because we're going to square this radical 5, that's going to be 5 minus x squared. And so we have essentially cosine to the 3rd, cosine to the 5th. And so cosine of this angle is going to be adjacent over hypotenuse, so that's going to be radical 5 minus x squared all over radical 5. Maybe you're not used to writing it in that term, and if we were to multiply both the numerator and denominator by radical 5, we would have essentially the square root of 25 minus 5x squared all over 5. And so these are going to be, each of these will be cosine of theta, so then we get the following, and this will be indicated in a different color. Let's use orange. So we have negative 5 to the 5/2 power, 1/3 square root of 25 minus 5x squared all over 5 to the 3rd power minus 1/5 square root of 25 minus 5x squared all over 5 to the 5th power, and the plus c. So you could work through all that to try to figure out what this term will be if you try to ever simplify it algebraically. So to recap, anytime the x squared term is being subtracted from another term and we can't do the simple u substitution, then we have to do x is equal to sine of whatever this radical of this number, sine theta. So the next set of problems that we see is going to be the case when you have two squares that are added under a radical.